Now, continuing our study of clusters of galaxies, let's consider their content. First, the X-ray gas. The origin of it is free emission, meaning scattering of electrons on protons in fully ionized plasma that has temperatures of tens of millions of Kelvin. And in fact, X-ray emission from clusters is so conspicuous that now there are surveys for clusters that are based exclusively on their X-ray emission. So whereas we use approximations, spherical symmetry and such, in reality we see features in the X-ray gas that show us that clusters are not yet fully formed or relaxed. They differ from cluster to cluster. So for example, if you had a group of galaxies fall into a large cluster, there will be a shock wave as the intergalactic medium of both collides. In the centers of clusters, there is a possible phenomenon called the cooling flow, and it works like this. Gas emits radiation, cools. Because of that, it will fall towards the middle of the cluster, where it will heat up again, because the X-ray emission is proportional to the square of the density, and so on. And so in early estimates, people thought that their clusters are having X-ray gas flowing to the middle, not because of gravity, but because of temperature differential at some rapid rate. And it was a real puzzle, where does the gas go? Now we know that this is only partly correct, and there are feedback processes that reheat the gas so that cooling flows are not quite as important as people once thought. So where does the gas come from? Some of it simply came from the intergalactic space, and some of it was expelled from galaxies in the galactic winds driven by supernova explosions. And the reason we know this is that the gas is not pristine. It's not just hydrogen and helium, but it contains metals, and roughly at about abundance of 1/3 solar. So we know that some of that gas came through chemical evolution in stars, in galaxies. And the X-ray properties correlate fairly well among themselves and also with other physical properties of clusters. Let's look at some of the X-ray pictures. The cluster on the left here shows a cometary-like thing, which is a bow shock from a clump of stuff falling through. The cluster on the right shows the strange filament, and we think that that's due to the jet from an active galactic nucleus. So they're not perfectly symmetric and homogeneous and so on, but by and large they can be, and so approximations are not so bad. And again, how do we determine masses? Simply applying the virial theorem that kinetic energy has to be 1/2 potential to within plus or minus sign, and we can consider galaxies as test particles using their velocity dispersion, or we can use X-ray gas as test particles, measuring its temperature. Either way, we measure kinetic energy per unit mass. And as you would recall, both of these methods yield the conclusion that the amount of mass in clusters is much higher than can be accounted by stars or gas alone. So therefore, there has to be some dark matter. This is how Zwicky originally discovered it. People actually do a little more sophisticated studies using X-ray gas and apply full-blown hydrodynamical models and so on, and that yields essentially the same results. So typically, in a cluster, 1/6 or so of the matter would be baryons, and the rest would be dark matter. And among the baryons, gas and galaxies, meaning stars, would contribute about equal amounts. Now, cluster collisions have recently led to yet another piece of evidence for the existence of dark matter. Here is one of those clusters which seems to have resulted from a merger of two clusters of galaxies. And the picture here shows X-ray emission as well as galaxies, but also dark matter, as inferred from microlensing studies around this merging cluster. So the blue shading indicates where the mass should be, and the pink one is where the gas is. You see that there is tidal shock, but also the two are displaced. Now, this is what you'd expect if the dark matter does not interact directly through electromagnetic radiation with the gas. The two clusters, which just kind of pass through each other, and eventually settle together into a merger. But the gas from one cluster collides with the one in the other and does not participate in this bouncing action. So you see the gas is concentrated towards the middle, whereas the dark matter halos of clusters are now separated apart. There are now several cases of these known, and they all yield the same results, that indeed mass-to-light ratios of clusters are several hundred times the solar mass-to-luminosity ratio, which implies, again, that there must be a significant non-baryonic component. When we talk about numerical simulations, I've shown you some of the modern hydrodynamical simulations, and these are now deployed to study evolution of clusters, including their mergers, the effects of active galactic nuclei, star formation, stellar winds. These are some snapshots of one of those simulations showing various physical properties. I mentioned that properties of clusters correlate with each other, and what's shown here is plot of mass inferred from virial arguments versus temperature. Now these trends look too good, and the reason for this is that we actually use temperature to infer the mass. But intuitively, this is exactly what you'd expect. The more massive clusters will have deeper potential wells, which will require higher velocities of particles, which means higher temperature, and that's exactly what we see. Likewise, X-ray luminosity itself is proportional to temperature and time power, and X-ray luminosity also correlates with cluster mass. Now, this is reassuring to know. It's not terribly surprising. It would be very surprising if they didn't correlate, but it's good to actually measure it. So how do we study properties of clusters as a population? Well, we can form their luminosity function or mass function, usually in X-rays, and see how it changes as a function of redshift. And here is an example. And it goes in the sense that at larger redshifts, there are fewer, more massive clusters, which is exactly what you expect if the clusters are being built in time. It takes a while to build up the biggest ones. This opens possibilities for use of clusters as cosmological probes, because in models with lower density and or positive cosmological constant, there is more time, and so you expect to form more massive clusters earlier than you would in high density zero cosmological constant models. So simply by counting clusters through some luminosity or mass function as a function of redshift, you can constrain cosmology. And here are the examples of cluster mass functions from X-ray measurements in two different redshift shells. The one on the left shows the concordance cosmology model plotted against the data, and as you can see, it goes beautifully through the data points, which is in a sense another vindication for the concordance model. The one on the right has the same matter density, suppose we got that right, but suppose there was no dark energy, and you can see that it fails completely in predicting the abundance of clusters at large redshifts. So just as we did before, combining constraints from microwave background, from supernovae, from baryonic acoustical oscillations, and so on, cluster measurements can be folded into the same type of statistical analysis. And, beautifully enough, their error ellipses cross exactly where all other methods cross. So they improve our knowledge of cosmological parameters, but also because this is a completely different way of measuring them, they give us an extra confidence that we've actually done a good job. Now let's turn to galaxies in clusters. One thing that will happen as a galaxy, like a spiral galaxy like Milky Way, plows through that X-ray gas, it'll get stripped away of its neutral hydrogen just because of the Ram pressure stripping. And that's indeed what is observed. The most gas-deficient spirals are found near the cores of clusters of galaxies, whereas those on the outskirts look pretty much like spiral galaxies in the field. The strength of this effect, the intensity of stripping, if you will, is proportional to cluster X-ray luminosity, which is, again, what you expect because it's the X-ray gas that strips away the neutral hydrogen as galaxies ram through it. And if you look carefully within individual spiral galaxies, the stripping occurs primarily in their outer parts, which are less tightly bound to the galaxy itself. So here's the plot of the hydrogen deficiency versus X-ray luminosity, and deficiency goes from no hydrogen removed to all hydrogen gone, and that correlates beautifully with X-ray luminosity of clusters, which is measure both their mass and simply the density of the gas. So here is a very instructive map of vertical cluster galaxies in neutral hydrogen produced by Jacqueline van Gorkom and her collaborators. These are contour maps of the neutral hydrogen density in galaxies. And M87 is the big galaxy in the middle, essentially the center of Virgo cluster. And it's an obvious effect that the closer you get to the cluster core, the smaller disks look in neutral hydrogen. So this is exactly what you expect if they're being stripped by falling through the cluster intergalactic medium. So gas collisions will strip away gas. What happens to stars? Gas will not affect them, but you may remember in numerical simulations, as say these galaxies merge or just pass by each other, their tidal features, and some number of stars in these galaxies will get unbound gravitationally. But they're still bound to the cluster. So they no longer belong to a galaxy now, they belong to a whole cluster. And they'll tend to accumulate in the middle, but because galaxies interact everywhere, you expect some diffuse light. And in fact, this is what was seen. First in Coma cluster, and here are the contours of very subtle low surface brightness distribution of stars, whereas galaxies are all under very high contrast, look burnt out. And another one for Virgo cluster. The big holes are where luminous stars and galaxies are, but you can see their features and in the slide which probably correspond to the tidal tails and streamers as galaxies interact. So the whole picture holds together very well. So let's recap what we learned about clusters of galaxies. They are the most conspicuous part of the large-scale structure, and they represent stage where structure becomes virialized gradually. Typically a few megaparsecs across, they have hundreds or thousands of galaxies in them. The mixture of luminous and dark matter in them is exactly what is the overall mix from cosmological measurements, baryonic to dark matter, non-baryonic dark matter component. The presence of the hot X-ray gas opens ways of finding them, such as simply X-ray emission or Sinaev-Zeldovich effect, which is popular because, as you may remember, it does not depend on redshift. The source is not the cluster, the source is the microwave background, and clusters just provide X-ray shadow for a background. And whereas galaxies have by and large fully formed, except for an occasional merger or so, clusters are very much still forming. And this is a process we now understand very well, thanks to the numerical simulations. Because of the dense environment, both proximity of many other galaxies to zip by or merge with, and the dense intergalactic medium of X-ray gas, galaxy evolution is affected in clusters. It proceeds a little differently from galaxy evolution in general field, because there are more galaxy encounters, some of which result in merging. There is certainly stripping of gas, which removes fuel for star formation, and so on. So we do expect, and we actually observe, differences in galaxy evolution between clusters and the general field. So next, we will start talking about properties of galaxies themselves.